Okay, in this video we're going to look at example 3.8 from Shigley, also from my notes, and it's basically taking a structure that has a lot of twists and turns to it and applying a load to it, and then calculating combined stresses because of the multiple effects of the load happening over at various cross sections. And so if we look at the problem statement, it says it shows a crank loaded by the force. It causes twisting and bending of a shaft fixed to the support. Okay, in actuality the support may be an inertia, so this may actually be rotating instead of being fixed, but we're going to treat it as a cantilevered wall. It says draw separate free body diagrams for the shaft from between A and B, okay, and the arm BC, so separate free body diagrams for those, and compute the values of all forces, moments, and torques that act. Label the direction of the coordinate axes on these diagrams. And so once we've done those free body diagrams, then compute the maxima of the torsional stress and the bending stress in the arm BC and indicate where these act. Okay, so the maxima of the torsional stress and the bending stress. And in arm BC, of course, our bending stress will be where the moment is greatest. Our torque is going to be constant anywhere along this arm, so there is no place where it's a maximum. It is a rectangular cross section, so we are going to have a look at calculating the torque in a rectangular cross section. And so, getting into the problem, we will first, be nice if we were if this were built up a little bit bigger, but going to BC, and I've got the picture down here where we can see it. Okay, if we just cut BC out all by itself, then what we're going to have at this end, right on the if we cut it right on the top surface of this round shaft, all we're going to have is a torque that's being caused about this section, no bending moment in any direction, and that torque will be the 1.5 times our load of 300 pounds. The author shows that right here as a torque, which is operating, being applied to the part in the direction shown. Point your thumb in the direction of that thing, curl your fingers, it tells you the direction of the torque. And then these would be resisting that torque. And so we're going to have the same torque on the other end, equal and opposite. Let's see, we're also going to have a shear force here acting downward on this end, same shear force acting upward on this end, but this force is also going to cause a bending moment. It's going to cause this bar to bend downward, so it'd be a bending moment about the x-axis. Let's see, that would be the, a little bit hard to see, let me scroll to the other one. That was called the x-axis, that's right, so that's called the x-axis, and that moment would be the 300 pounds times this overall length, which is 4 inches, and so that moment would be a 1,200 pound, and that was called MX. Actually, probably called MB. Where is it? MB, 1,200 pounds, 1,200 pound inches. Okay, and so that takes care of the free body diagram of section BC only, and then section AB only. And at the B end, because of this force here at the B end, we're going to have a torque. We're going to have a small bending moment about the Z direction. Let's see, are we going to have any other bending moments? No. A torque and a bending moment about the Z. This one we're going to also have a torque and a larger bending moment about the Z, and we're going to have a shear force at both locations. Let's have a look at it. Okay, so at the end B we have a torque, which is the 4 inches times the 300 pounds, that's 1,200. We have a bending moment because of the load applied here, and that distance 1.5, so we have 300 times 1.5, which would be what, 4.5, 450 bending moment. We have the shear force acting straight down at this end. We have the shear force equal and opposite at this end. We have the same torque here that we have here, equal and opposite. and we have a bending moment right here, which is the distance 5 inches plus 1.5 inches. That's 6.5 times the force of 300, and that sounds like the 1900 inch-pound force bending moment indicated right here. So that would be the part A of the question. Draw free body diagrams showing the loads, and then let's see, what was the next part of the question? Compute the maxima of the torsional stress and bending stress in arm BC and indicate where they act. Okay, and so our bending is going to be worst at point B because that's where our bending moment about this x direction would be the largest. And so we'll calculate the bending stress as MC over I, and our bending, let's see, BH cubed over 12 would be the moment of inertia, where that tall distance would be cubed in the BH cubed over 12. They've already done a little bit of work because they said that C is H over 2, and so that H over 2 cancels one of the H cubed here, and the 2 interacts with the 12 to give a 6. And so 6 times the moment over BH squared is equivalent to MC over I. And our moment at this point was the 300 pounds times 4 inches, or 1,200 pound inches. And so we get an MC over I stress of 18,400 psi. Now, in addition, we want to calculate the maximum shear stress because of torsion, and we're not going to use TR over J because TR over J only applies to circles. Instead, we'll use the formula which is T over BC squared, and then actually let's go back and find the formula and the correction table. So either T over alpha BC squared or a close enough approximation, which then avoids this table, this alpha thing, is T over BC squared 3 plus 1.8 over BC, which avoids having to look up alpha, or this is alpha, or at least an approximation. And so T over BC squared 3 plus 1.8 over B over C, where again, looking at the table, we got to remember this configuration. B over C is always a number bigger than 1. So B must be bigger than C. So in this case, the B would be the inch and the quarter. The C would be the 1/4. Hope you're not getting dizzy with all the scrolling that I'm doing. So B over C is 1 inch and a quarter divided by the 0.25, B over C. Here's BC squared. Plug that in, and we get a 19,400 psi torsional shear stress acting everywhere along the length of this thing because the torque is uniform. Let's see, they're going to point A. Why do we go to point A? Compute the maximum of the torsional stress and the bending in arm BC. Was there a C part to this question? I don't remember it, but it's certainly reasonable that we would go back to point A, calculate MC over I, and it's circular. So we have to remember the formula for I, which is, let's see, pi d to the 4th over 64, I believe, and we lost that. The 32 was the 64 divided by 2 from the I over C computation. And we also have TR over J for the torsional shear stress at point A, getting 47,000 and negative 14,000 psi, and then combining the stresses at point A, we're going to get principal stresses of, let's see, and we're using the plus sign, of 51.2 kpsi and a maximum shear stress of 27.7 kpsi combined at A. I don't quite remember why we did that because I'm not sure that the problem asked for it, but very reasonable thing to do. And let's just look, what about stresses at A compared to stresses at B? Stresses at B were pretty small. an 18,400, a 19,000, but that bending at point A really dominates in this problem. So that would be the end of this problem.